is 1, 2, 3. So 1, 2, 3. So we're here. So in the last term, it's going to be plus, again, 1/4 times 3 factorial x minus 2 to the third power. And those are the first 4 terms we're looking for. So if they ask for 5th terms, we're going to have to do one more. And that's how we combine this situation with something called the Taylor series itself. Now, let's make this a little easier and do example 2, but now we want the Maclaurin series. So therefore, notice when it comes to the Maclaurin series, they will never tell you center that because it's automatically a is equal to 0, right, when it comes to it. Okay. All right, so for number 2 says, find the Maclaurin series for the function e is equal to negative 2x, and also find its radius of convergence. Okay. Well, first, let's find the Maclaurin series. Now, notice it said it didn't find the first 4 terms. We want the general Maclaurin series, what's always going to be itself. So this one's going to be a little bit more work going by that. So, but it's still not too much process to deal with. So first, find f of 0, right? That's the first term of our Maclaurin series. So plug in 0 in for x. So it's e to the 0 power is just 1. Okay, taking the first derivative. So taking the derivative of this is going to be negative. Right, take the derivative of the inside times the derivative of the outside, which is just itself. And then plugging in 0 is going to just give you negative 2. Take the second derivative. And we do this until we get an actual pattern, or you could see an actual pattern. So now we take this derivative. It's going to be positive 4 e to the negative 2x. Plug in 0. We get 4. Take the third derivative and just keep going until you can actually see a pattern evolving here. Okay. So let's see. According to our sequence, it's equal to 1 minus 2x, and again, I'm just following the Maclaurin process here. So that's the 1 times first derivative divided by 1 factorial plus second derivative at 0 divided by 2 factorial. So in this case, it's going to be 4 x squared divided by 2 factorial minus negative 8, or I'll just put plus here, minus negative 8 x to the third divided by 3 factorial. And lastly, plus 16 x to the fourth over 4 factorial. And again, the whole process is finding a pattern in this process here. Okay. Now, first thing, we know it's going to be n factorial on the bottom because it just follows that template there, right? This is 0 factorial, so that's a good thing. Check that out of the way. Okay. We also know it's going to be x to the n power because that's always there as well, which is great. Okay. And notice it alternates from positive to negative, positive to negative, positive, negative. So therefore, we know also this is going to alternate. Okay. And we'll start at 0 because that's where we usually start at. So that checks out. So now the last thing is, how do we go from 1 to 2, 4, 8, and then 16? Okay. And now notice we're multiplying by 2 every single time, right? 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, so therefore the next one is going to be 32. So we're always multiplying by 2's, or multiplication is technically the powers themselves. So this is actually 2 to the n power, because 2 to the 0 power is just 1, 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power. So there we go. So this is our Maclaurin series for this function. Okay. Now, unfortunately, we're actually not done here, because they also asked us to find the radius of convergence. All right, so to do so, whenever you want asked to find radius of convergence, always go back to the definition and either use the root or the ratio test. And in this case, we're going to be using the ratio test to do so. So the ratios test, if you don't remember, is taking the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So in this case, a sub n plus 1 is just adding 1 to all the n's. So it'll just look like this. Like that. And then a sub n is just that itself, right? So I'll just do that little trick and see what we get there. So take the absolute value. And the good thing about absolute values is these actually go away because we're taking the absolute value, right? So it's not altering anymore. So really you could just cancel those out itself when it comes to it. Okay. And now we can just focus on those portions. So like we did in that section, this is technically 2 times 2 to the n. And this is technically x times x to the n all over. And again, I could break this up into n plus 1 times n factorial. And then technically it's division, so right, it just flips it. So I'll just skip that initial step. And then at this point, we just simplify as best we can, right? So notice n factorials cancel. X to the n's cancel, 2 to the n's cancel, and there we go. So what do we get next? So taking the limit as n goes to infinity of what do we have going on here? We have 2x over n plus 1. And we know this always goes to 0, right? Because this is technically 1 over n plus 1. So if you're not sure why that is again, this is technically looking like this. And this is the only thing that's going to infinity, or n is going to infinity, so this doesn't do anything, and this goes to 0 no matter what, right? So remember those cases. So in this case, the radius convergence is for all x. So for all x, this works. So there is no radius of convergence. Any x value will make this type converge. Okay. So fun little fact there, right, when it comes to it. Okay. So the last part of this section is, okay, what if we know, which is the best part, what if we know some Maclaurin series, and is there a way we can use these to help ourselves out? So this entire list here is known Maclaurin series. So we know, and we're going to use these to help ourselves out in general. So find new ones based off these situations. We're just going to tweak them. Okay. So again, you never have to prove these. I know if we would be in class, you may have to prove that this actually does work out. You know, what I mean by proof is using the definition of a Maclaurin, show that this ends up being exactly this series and so forth. But since we're online, you know, you guys will be given this already, so you guys can use this to help yourself out, you know, already when it comes to it. Okay. So now what we're going to do is, okay, using these series already established to us, is there any way we can use this to now find creations of others? And again, it's also given with this respect to radius all the way down here. Okay. The only one we really haven't too much talked about is this one. And this is called the binomial series. Again, we're not going to go too much in depth. As binomial is like, x plus 1 to the 8th power. How do you expand it? You guys probably saw that in pre-cal. It's called the binomial theorem. How to expand a series itself. That was basically a series in disguise way back in pre-cal. Okay. So what this process is given all of these, is there any way, if I tweak them, I can now rewrite a new series based off this information? Okay. So let's look at example 3 here to see that. So again, the key thing is these are all Maclaurin series, not Taylor series. It's a key thing. Be careful about that. Okay. All right. So this one says find the Maclaurin series for each and find the radius of convergence. So the first one's on the down here is, so we want to find, just like the last question, the Maclaurin series and its radius of convergence. So this function is the natural log of 1 plus x squared. Okay. All right, so if we go up here, the question now is, can we use any of these to help us find this one? Okay. Well, if we look, it looks like that we may be able to use this one. Right? We have natural log of 1 plus x, but now we just want x squared, which hopefully wouldn't be too bad, right, when it comes to that concept. So this is how we're going to use this one to evaluate this one. Notice the only difference between what we have and what we're given here is this is an x squared and this is an x. Okay. So how we use this power series is all we're going to do is replace x squared everywhere we see an x. Or in other words, we're just going to square everything. Again, what I'm saying is everywhere we see an x in this series, we're going to replace it with x squared because that's exactly what we want here. Okay. So again, if we just follow the template, instead of x, it's now x squared. So this ends up being x squared. Over here, it's going to be being a minus x squared squared over 2 plus x squared to the 3rd power over 3 minus x squared to the 4th power over 4. And again, dot, 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 dot. Keeps going in that process. Okay. So what does this series actually look like? Well, notice the only thing we changed is instead of x to the end is now just x squared. So this ends up being the sum of negative 1 to the n minus 1 over n factorial. And again, the only thing we changed, instead of x, it is now x squared n. And there you go. You're basically done. Now, again, in the back of the book, they may want to, if you show the answer, they might make this a little nicer to look at. So essentially, it should look like this. But either way is fine. So all I did was multiply n times 2, which is just 2n. Okay. And that's it. That's how we find the Maclaurin series using known ones. Somehow we're going to manipulate it, or just, in this case, we just plug in x squared instead of x and see what we get there. Okay. And then the last part, we want to find